What is up, everyone? It's Mr. Holtz. Today we're going to be talking about periodic trends. And what I mean by periodic trends are things that we find when we are looking at the periodic table, and the characteristics about these elements are based on the slight changes that we see depending on whether we're moving left to right or up and down within the periodic table. And we'll see how the different parts of the structure of atoms influences their characteristics. All right, so let's dive right in. Okay, so bit of review just to be aware of. Valence electrons, okay? A lot of stuff we're going to be talking about today has to do with valence electrons. So keep in mind, valence electrons are found in the outermost energy level, okay? When we're looking at Bohr models and we're talking about the rings of atoms, right? The valence electrons are the electrons in the outermost ring of that atom, okay? Different energy levels can hold different numbers of electrons. So it's related to the structure of the periodic table, right? The first period on the periodic table just has two elements, right? Hydrogen and helium. So the first energy level, when we're talking about Bohr models of atoms, only has two electrons in it. They're only valence electrons if we're talking about hydrogen or helium, because once we move on to other atoms, those electrons are still there, but they're not in the outermost energy level, so they're not considered valence electrons. Okay, so keep that in mind. We're going to talk about this once we get there, but keep in mind, an ion is an atom that has gained or lost valence electrons, giving it a charge. Basically, you don't have the same number of protons as electrons, which means your positive charges and your negative charges are not equally balanced out. So an ion is an atom that has a charge. Doesn't necessarily mean that it's positive or negative, and we'll look at those as we move throughout the year. Okay, so let's look at our first periodic trend here, which is going to be atomic radius. All right, so atomic radius is pretty straightforward. It's pretty much exactly what it means. If you know about circles and spheres, they have a radius, but it's basically the center, the distance from the center of the nucleus to the edge of the electron cloud. Now, we haven't really talked about the electron cloud as opposed to electron orbitals or rings around Bohr models, but we could just think of the edge of the electron cloud as the furthest edge of the valence shell. Okay, so let's take a look at that. All right, so again, here's a circle. Now, if we wanted to think of this as a Bohr model, right, the center would be our nucleus. Here's our valence electrons in our shell on the outside, and obviously the radius is just the atomic radius. Okay, that's what that means. But let's take a look at what that trend looks like when we're going across the periodic table, and then what happens when we go down the periodic table, because it's not super intuitive. Okay, so down a group, right, from top to bottom in a periodic table, it increases. Atomic radius increases, meaning it gets bigger, right? The radius gets bigger as we move down the periodic table. Now, let's talk about why. Well, keep in mind, each step down as we go down every single period from period 1 to 2 to 3, etc., in the periodic table, we add another energy level, right? Every time we move down a row in the periodic table, our Bohr model would get a new shell on the outside. Okay, so because it gets a new shell, it gets bigger, which makes sense, right? So compare the radius of this atom with just one ring of electrons to the radius of this atom with two rings of electrons. Okay, obviously the radius of the atom with more rings is going to be a greater radius. So it makes sense that as we go down the periodic table, atomic radius increases because we're getting more rings, we're getting more shells of electrons. All right, now let's look at, not sure what's going on with this here. Okay, so let's look at what happens as we go across the periodic table, okay? So as you can see here, atomic radius actually decreases, which might not seem super intuitive, but let's take a look at why that is. So keep in mind, as we move across, meaning from left to right on the periodic table, electrons are being added because we're still going along the same energy level, right? We're still adding more electrons. So it's not that we're getting more shells, but electrons are not the only thing we're adding here, right? As we get bigger and bigger atoms, every time we get a new atom, keep in mind that the atom is identified by its number of protons, right? By its atomic number. So as we move across the periodic table here from element 1 to 2 to 3 to 4, etc., as we move from left to right, lithium to beryllium, we get an extra electron, we get an extra proton in the nucleus. From beryllium to boron, we get another electron in that one ring. Okay, we're still on the same energy level of electrons because we're still in the same row on the periodic table, but we also get one more proton in the nucleus. Okay, same thing happens as we continue. All right, So let's think about what the effect would be on the rings of electrons as we get more protons in the nucleus. Well, as we move across, all right, like I said, we get more protons, more electrons, more neutrons, but the neutrons don't have a charge, so we're not really concerned about their effect right now. They don't really influence it. But keep in mind, we have the same number of rings of electrons, okay? So if we look at an example here from sodium to argon, let's go back to the periodic table. Okay, here's sodium, period 3. Argon is still period 3, but they're on the far ends of each other, okay? So sodium, as we can see, has 1, 2, 3 rings of electrons, but it only has one valence electron in its first shell, or its outer shell, excuse me. So its valence shell has one electron in it, okay? And there are 11 protons in the center because its atomic number is 11. Now, if we move all the way over to argon, we still have 3 energy levels, but we can see that the energy level on the outside, and I know I didn't really draw this to scale, but hopefully you can see that this radius is smaller. Well, why would this radius be smaller? Here we have 8 valence electrons, which is great. Okay, we've just been adding those electrons to the valence shell, but we also have 18 protons. Okay, so we have not gained any extra energy shells. We don't have any more rings of electrons around this atom, but the center in the nucleus has 18 protons now. Okay, 18 might not seem like a lot more than 11, but the issue is here that now our nucleus has a way higher positive charge, right? Keep in mind, protons have a positive charge. And because electrons and these rings of electrons have a net negative charge, then the positive charge of the nucleus in the center is going to be pulling the electrons in from the outside. So you can think of it as we still have the same ring of electrons, but as we add more and more protons in the nucleus and compare that to the same ring of electrons, it really just pulls that ring in a little bit more each time we add a new proton because the charge of the nucleus is getting stronger. Okay, so let's take a look at what that effect has on this trend. Okay, so here's a generic look at the atomic radius of all these different atoms in the periodic table. And you can see that just like what we talked about, as we go from top to bottom, as we go from one period to the next and we're gaining more electron shells in the atom is getting bigger, right? The atomic radius is increasing. But as we go from left to right, you can see that the atoms look like they're getting smaller. We still have the same number of electron shells, okay? The valence shell is still in the same place, but because the nucleus is getting stronger and stronger and stronger by adding more protons, it's causing the valence shell of the electrons to get closer and closer and closer to the nucleus. So we're not gaining or losing any more shells, but the outside, the valence shell, is still shrinking because of that increased nuclear charge, okay? All right, before we move on to the next periodic trend, there's one concept we need to understand, and that's called electron shielding. So as more energy levels are added to atoms, the inner layers of electrons shield the outer electrons from the nucleus. Okay, electrons are held less tightly to the nucleus. So let's take a look at this effect. All right, electron shielding. Basically what this means is as we get more and more shells, then that effect of the nucleus decreases as the distance to the valence shell increases. Okay, so for example, here in this first atom, we only have one valence shell, okay, which means it's super close to the nucleus. So the nucleus is pulling really strong on these electrons because they're the only ones there. So they're the only ones to feel the pull from the nucleus, right? The nucleus has a positive charge, the electrons have a negative charge, so they're being pulled in by the nucleus, okay? Now this is going to have a really strong interaction here, okay? Greater attraction between valence electrons and the close nucleus. You can see how close this nucleus is to these atoms, or these electrons, excuse me. Okay, so think about how hard it would be to remove either of these electrons from that shell. Now, with something like this much, much bigger atom here, you can see that there's now 1, 2, 3, 4 rings of electrons. So the positive charge of the nucleus is pulling all 4 of these shells towards it, but the effect of that charge is spread throughout all 4 of those rings, which means that by the time the force gets to the outer ring, it's not as strong as the first ring feels. Okay, so the first ring feels a strong pull from the nucleus because it's right next door, but as you get further and further away from it, these rings don't feel like the nucleus is pulling on them as strong, all right? So there's a lesser attraction because in this scenario, the nucleus is further away, and there are three other rings of electrons before you reach the valence shell. So compared to our first example here, this valence electron or this valence electron would be much easier to remove from this atom because they're not being held as tightly by the positive charge of the nucleus. Okay, so that's what electron shielding is, and that will influence the other periodic trends that we'll take a look at. All right, so let's go back to these slides. And the next periodic trend we want to talk about is ionization energy, okay, which basically means the energy that would be required to turn an atom into an ion. Okay, so as a refresher, what is an ion? And again, I'm not really sure what's going on with my screen here. Here we go. Okay, so ionization energy, which basically means removing valence electrons. Okay, so in this case, an ion is an atom with an unequal number of protons and electrons, an atom that's charged. So technically, you could have a negatively charged ion. You can also have a positively charged ion. It depends on whether or not you have more protons or more electrons. Now, when we talk about ionization energy, we're only talking about what happens in terms of removing valence electrons. So in this case, we are creating an ion by taking valence electrons away. So let's take a look at this trend. Okay, so it is the energy required to remove an electron from an atom. Okay, that is the definition of ionization energy. So the larger the atom is, the easier its electrons are to remove, which hopefully makes sense because this is coming straight from what we talked about with electron shielding. Okay, so going back to this example here, with a small number of rings of electrons, obviously the valence shell is closer to the nucleus, which means it's being pulled in really, really strongly by the protons. So it's going to be really hard to remove any valence electrons that are super close to the nucleus. Whereas if there's an atom that's really, really big and has lots of shells around it, then because that strength of the nucleus kind of decreases as we get further and further away from it, right? That electron shielding, the force is being spread out through all of these different rings. These two valence electrons are going to be a lot easier to pull off of that atom because the attraction between the nucleus and all the electrons in the valence shell, since they could be really, really far away, that attraction could be really weak compared to electrons that are really, really close to the nucleus. Okay, so the larger the atom is, meaning the more shells of electrons we have, the easier it is to remove electrons from the valence shell. All right, and that's really just based on the electron shielding that we just talked about. Okay, so ionization energy decreases down a group, which is exactly what we were just talking about, right? The larger an atom is, the more rings of electron an atom which is what happens as we move down the periodic table. The more rings of electrons an atom has, the easier it's going to be because the electron shielding is spread throughout more rings of electrons. Okay, valence electrons are easier to remove because inner electrons shield outer electrons from the attractive force of the nucleus. Therefore, it requires less energy to remove those valence electrons. Hopefully that's pretty straightforward. Okay, it also increases across a period. Why? Well, protons are being added to the nucleus, which increases the nuclear charge. Okay, so this is related to what we were talking about in terms of why the atom shrinks as we move across, right, from left to right, across the periodic table within the same electron shell. Okay, the charge of the nucleus is getting stronger. Let's take a look at this. The charge of the nucleus is getting stronger. Not sure why my screen's doing this. The charge of the nucleus is getting stronger compared to the same energy level of electrons that we're looking at. Okay, so it's going to be harder because this ring of valence electrons is feeling a stronger pull from the nucleus than it would be if there were only a few protons in the nucleus, or fewer protons in the nucleus. Okay, so here's kind of a representation of ionization energy. So hopefully you can recognize that on average, as we move from left to right, the ionization energy is increasing. So it requires more energy to take electrons away from the atoms on the far right side of the periodic table. And as we move down the periodic table, it's getting less. because as we get more rings of electrons, it gets easier to pull off one valence electron from that outer shell. All right, so the last periodic trend we're going to look at is electronegativity. So electronegativity is, just like it says here, is a measure of an atom's attraction for another atom's electrons. Now, this is kind of a difficult concept to understand based on this description, but it's basically how likely is it that one atom will take an electron from another atom? And we'll look at the trend, but keep in mind, this is a super important topic in chemistry. Okay, when we talk about what kinds of bonds are we forming between atoms, whether molecules are polar or nonpolar, different interactions between molecules and other molecules, and the intermolecular forces that we'll get to, almost everything comes down to electronegativity. If at the most fundamental level of chemistry, everything is based on this concept. Okay, so again, it's how likely is it that any given atom, when it interacts with another atom, will it take one of those valence electrons away? Now, we measure this on an arbitrary scale, and we usually just base it off of what is the one atom that's most likely to take any electron away from anything else, which ends up being fluorine, compared to atoms that don't really take any electrons away. And again, as we look at this trend, we'll take a look at why that is. But generally, metals are electron givers, which means they have low electronegativities. They're unlikely to take electrons away. And nonmetals, things like nitrogen, oxygen, fluorine, the halogens, they are electron takers, and they're more likely to have high electronegativities. Okay, they're likely to take electrons away from other atoms. We don't really talk about noble gases in terms of electronegativity because, again, keep in mind, noble gases have filled their valence shell. So because there's no space in that ring, in that valence shell, for extra electrons to go, we don't really think of noble gases as having an electronegativity. They also don't form bonds with other stuff. So we don't really think of this concept in relationship to those kinds of elements. All right. Okay. So electronegativity, and we're going to start here looking at what happens when we go from left to right across a period. They increase. The electronegativity increases, meaning the likelihood that these atoms are going to take electrons from other atoms increases from left to right. As we move from one to the next, to the next, to the next, to the next, as we get close to filling our valence shell, it's more likely that these atoms on the far right side are going to take electrons from other atoms. So let's take a look at why. Okay. So the easiest way to think about it is that electronegativity is based on the concept that in chemistry, there is a relationship between atomic stability, how stable an atom is, and how close it is to filling its valence shell. Okay. So if an atom is pretty close to filling its valence shell, it's really going to try and do so, even if that means it has to steal something from someone else. So let's look at fluorine here. Okay. Fluorine has obviously its first shell full, but its valence shell has 7 electrons. Okay. 7 valence electrons, because fluorine is one element away from being a noble gas. Okay, it has one spot to fill its valence electrons in its outermost shell. So because fluorine is so close to filling its valence shell, and it has a really strong nuclear charge, right? As we move across, the atomic radius shrinks because the nuclear charge is stronger. So it's not really likely that fluorine is going to want to give up any of its electrons, because it's only one electron away from filling this last spot right here, which means fluorine is really, really likely to take electrons away from other atoms, partially because of how close its valence shell is to the nucleus, and partially because it only has one more electron to fill its valence shell in the first place. So if we compare that to lithium, so if we go over here and look at lithium, notice lithium is the first element in the second row on the periodic table. Okay, it only has one valence electron, and it's pretty close to the nucleus. However, here's lithium, right? It has one valence electron. If we're trying to get atoms to fill their valence shell, it's not very likely for lithium to try and steal 7 electrons. That would be a lot of work for this atom. So what's more likely is that lithium's just going to say, you know what? it's not really likely that I'm going to be able to steal 7 electrons from other atoms, because that's a lot. 7 electrons is a lot. That's more electrons than lithium even has to begin with. So you know what I'll do? I'm just going to get rid of this one. I'm just going to give that electron away. So lithium is a metal. If we go back to these notes, you'll see that metals are electron givers, right? They have low electronegativities. And part of that reason is because since metals are on the left side of the periodic table, they really don't tend to have a lot of valence electrons. They have maybe 1, 2, or 3, and it's easier to give up 1 to 3 electrons than it is to try and steal 6, 7, or 8. All right, well, obviously not 8, but 5, 6, or 7 electrons. So if this electron goes away, another atom would be stealing that, right? So fluorine would actually be a great example of something that would steal this electron. So because lithium is not as far across, right, has a larger atomic radius, so the nuclear charge isn't as strong, and it's not very close to filling the valence shell that it already has, it's more likely to just give that electron away, all right? So electronegativity increases across a period. Now, talking about going down a group, right, from top to bottom in the periodic table, electronegativity decreases. Okay, and again, this has to do with electron shielding. If these atoms are trying to fill their valence shells, because of electron shielding, because of this electron shielding, even if this shell only requires a few more electrons, it's not going to be as big of a deal to fill this for an atom that has anywhere from 4 to 6 rings of electrons compared to something like fluorine that only has 2, right? This does not have the effect of the nucleus is pulling much stronger on this valence shell of electrons than it would be with something like this, okay? So because that effective nuclear charge, the positive charge in the nucleus, is spread out throughout all of these shells of electrons, this atom isn't going to be as concerned to fill that shell because the charge of the nucleus is spread throughout the atom. So I find it a little bit harder to conceptually explain the trend for electronegativity, but if you take a look at this picture, all you really have to remember is that it increases up and to the right. Okay, so if you know that fluorine is the most electronegative atom on the periodic table, and this element down here, which is called francium, has the lowest electronegativity, then knowing that the trend moves in that direction should be the basis that you need, as long as you can relate it to that electron shielding effect that we were talking about earlier. Okay, so again, here's a great picture that represents the relative electronegativities from one atom to the next. And you can see that as we move from kind of the bottom left up to the top right in the periodic table, those values for electronegativity increase, which means that the atoms over here, like fluorine and chlorine and nitrogen and oxygen, are much more likely to try and steal electrons from other atoms. And all of our metals like sodium, lithium, magnesium, calcium, these atoms are much more likely to give up their electrons, all right? So the last thing on here is just a refresher of the octet rule, because this relates to those periodic trends. But when we're thinking about the octet rule and thinking about having a total of 8 valence electrons for any given atom, this is really a trend that explains bonding patterns. And when we're talking about this, the atoms that we should really be concerned with are the nonmetals that kind of live right around here. Okay, things like our halogens, right? Fluorine, chlorine, bromine, iodine, things like nitrogen, oxygen. Phosphorus and sulfur can be a little funky sometimes, so we'll talk about that. Carbon's definitely a good one. But this mostly refers to the nonmetals that we're going to be talking about. And this is a concept that more applies to covalent bonds than it does ionic bonds, which we'll get into in Unit 2, so don't worry about that. But hopefully this was a good introduction to periodic trends. Again, go back and watch this as many times as you need. You can pause it while you're taking notes. But write down some questions so that when we're in class, you have things to ask. And of course, as always, make sure you guys hit that like and subscribe button and give me some love, and I will see you in class next time. Peace.